clearly artificial intelligence is really interesting and really important, but so is quality. So we wanted to have this session to explore some quality aspects of the fantastic revolution of artificial intelligence. So it's my great pleasure, first of all, to welcome Raluca Krisan, who's going to be talking about some ethical issues of artificial intelligence. So to you, please, Raluca, please introduce yourself. Thank you.
Hi, Shirley. Hi, everyone. Thanks a lot for having me to this talk. Hopefully, it'll be good, and we'll get some good questions in, and kind of start up a conversation. Just in terms of a quick intro from me. So I'm the CTO and one of the co-founders of a company called Ethic. I'm a data scientist. That's my background. I've been in the data space for 10 plus years now. Prior to Ethic, I was mainly working for consultancies, and my clients were mid-sized to large corporates. So a lot of different companies from eBay, BA, Sony, but also telco and lending. So a mismatch of things. And then a few years ago, we started Ethic to we really felt very strongly that there was a need for more tools in the market to address the trustworthiness of machine learning and AI systems. We thought that was very much an unaddressed problem. That's why we started to kind of build these toolkits and build the tools for people to be able to build more robust and hopefully ethical systems. So that's me in a nutshell. Moving on to kind of the topic of the talk and a little bit of an agenda. So I will spend quite a bit of time on why it is matter that these systems are robust and fair, and why actually robustness and fairness really are not mutually exclusive. On the contrary, they really go together. Then we will go to more kind of specific issues that the system, like specific system failures that then lead to these unethical and lower performing outcomes. Afterwards, we'll talk a bit about kind of more on the solution side, about our, what we believe in is around machine, this concept of testing for these AI and ML specific issues, and some different characteristics of testing and a bit of a description. And then we'll end with a bit of an ecosystem comments and just some general. Hopefully, we'll have some questions as well. I think the questions are at the very end of the session, of all three sessions, really. Okay, great. So yeah, I mean, I'm very much, being from an applied background, applied data science background, rather than a theoretical one, an academic one. I'm very much about examples, and really you can see in the examples why having fair systems matter. And there really are there are two dimensions to shall we say, well-performing AI systems. The first is around this notion of ethics and fairness, but the second is around the notion of performance, and the two really overlap. So some of these examples include the Amazon case, which was quite a while back, but I guess it has the benefit that it's one of the few publicly available cases. So they built a machine learning based system to kind of help them sift through CVs, to recruit people for the software engineer position. And unfortunately, like the kind of errors it came up with were so obvious that they had to kind of leave it behind and not use it. And the problem there was that they weren't really picking up any CVs for any women. I mean, that's quite hard to do. I mean, not like the kind of zero metric there. But it's in a sense, it's understandable. The data they had was very skewed and so forth. In a second way, they couldn't really use it, and it was like a fail, time and effort failure. and just wasted, right? The second one is a bit more, like the model actually did end up in production. It did have real world implications. And it's the case of the Apple Card, that basically in the US, the rates for the wife of the couple were 10, 20 times lower than the rates of the husband of the couple. We're talking about, couples that have same income, same credit risk scores. They might have lived in a common property state, and 10, 20 times is a really big difference. I mean, okay, 20% is not great, even 50%, but like 10, 20 times is a really big difference. So, the regulator was able to, had to, because of consumer complaints, the regulator ended up picking up this edge case. There's a lot of these occurrences that don't get picked up because the difference is not so big. But yeah, in this case, it was kind of an obvious one, and again, one of the few public cases. And two more, which I guess have to do, in a sense, these are all robustness performance issues, but these are clearly kind of robustness performance. So there was this was more of a business issue, but again, it's the quality of the system really led to Zillow losing about 500 million. They were a property trader, and their algorithm, unfortunately, didn't really cope well with changes in the economic landscape, which is very understandable. I think everyone who's built an algorithm in that space knows that's not easy to do. It's very hard. But then the problem is that this didn't get picked up. This got picked up like 3 months after the decay really started picking up. So that meant that they just lost a lot of money. I mean, had they were even a week later, it wouldn't have been great, but it would have been much, much better. Even 2 weeks, but 3 months is a long time, and it gives you a lot of opportunity to lose a lot of money. And going back again, this is a performance issue, but it's the impact. The impact on the subjects, the impact of the model depends on, I guess, what the model does. In Zillow's case, it really was just about money, but there are a lot of cases, especially public sector related or healthcare related, where it is about people. And there is unfortunately a very well documented case in the States where this algorithm used to, some algorithms used to predict the kind of readmission rate of specific patients to the hospital, right? So, is this person going to have the same condition again, or a similar one? It is unfortunately very much under predicting for certain demographic groups, which of course happen to be African Americans, kind of perpetuating the inequality aspect in the States. So these are some elements, the reason why I always start with these stories, because unfortunately these are kind of real life, public available information stories that show that the impact of these problems. And we're not talking about, the issues now that come from ChatGPT and all the large language models, right, which are, severe as well, but these are already have already been happening for a while, right? So this is not kind of unfortunately
Sorry,
a lot of practitioners.
No idea.
So yeah, and these are, like I said, public available, but I think all the, unfortunately, a lot of practitioners like myself have kind of seen this kind of in a real life context, and it's not, unfortunately, it is more widespread, and I think we all wished it were. Okay, now all these kind of real life, not terrible, quite bad outcomes come from specific system failures, right? So I mean, and I think the field has moved quite a bit in that it's able to really. And it has been able for a while, to be honest, but now, there's a lot more tooling and a lot more knowledge to really be able to identify the systems failure that cause these real life problematic outcomes, right? So these are some areas where failures occur. They're not exhaustive, but they're a good starting point. So the first one is around performance, and this is a lot around, and we see this a lot, especially in shall we say people-related use cases, where basically just the model really underperforms for one segment, and it's oftentimes hard to know in advance which one it's going to be. So that's not going to be necessarily specifically demographics. It might be a very specific demographic group from a specific region with a specific, I don't know, product holding, if it's a product company, or specific characteristics, right? So it might not be quite obvious what the group is, but it will, for some reason, whether it's data collection or the model itself is not really capturing things well for that group. Another area of problems is, this kind of catch-all phrase called drift that has become drift now, which is a lot around, data changing in once the model maybe the model was trained on some data, with some distribution, the world has changed, and the model doesn't really perform well anymore. And unless you have specific, monitoring in place, there's no way you're going to pick that up. And the known example very much is around COVID, right? When the retailers, they were predicting certain sales on pasta and toilet paper and all of that, and they had their stock for those sales, but people kind of decided to buy a lot more, and then that ended up impacting. And afterwards, some other issues happened with their supply chains and ended up impacting quite heavily. But in a sense, that was kind of a prediction failure. But understand again, all these failures are understandable. It doesn't make them still. The idea is that can we find a way to manage them or mitigate them as soon as possible, right? There is the understanding, especially with drift, that it's very hard to know in advance, right? Either you build like this perfect model, but you should be able to tell as soon as it happens, right? And then mitigate as soon as it happens. Another area is very much around explainability. And this is an area that actually most businesses find, like, how is explainability a system failure, right? And I mean, it's not in a way, but in a different way if the users around the model, whether they're business stakeholders or operations people or whoever they might be, are not really able to, or domain experts often, they're not really able to engage and interact with the model. The model doesn't make sense to them. What they're being told doesn't really align with their experience. That model isn't really going to get too far. And it's less to do, I think, this area is less to do with, the known pitfalls of deep learning and so forth. Like, it truly is very difficult, but it's to do with a lot of times to do with more banal reasons, like just the presentation layer and just some kind of basic care being given to having the model interact with humans, in a business or in a work context. And the fourth area is probably the most complicated, and we've talked about it briefly, like with bias, but it's not. I think bias a lot of the time it's again one of those catch-all phrases where it is a system failure in that one demographic group really ends up discriminated unfairly because of this model, and this is an purely unintended consequence of it, and it's also illegal. However, the cause, there's so many causes along the way why this could happen. So it's oftentimes not clear. The cause is not clear. The outcome is quite clear, but the cause is not clear. And for instance, sometimes it's not necessarily about data. It's about the way the system was designed. So the example here that I do like to give, because in a sense it does go a lot into kind of some very clear statistics, assumptions that maybe people don't kind of take into account when building these models for some reason. Although just because they're called ML or AI doesn't mean that they're necessarily they don't they don't need to obey some of the similar assumptions. And the example is that, quite a few years back, the city of Boston created this app to understand which roads in the city have more potholes, so they could kind of prioritize where to what to fix without having to send people and check out the whole city. And understanding, I guess, what roads which of these potholes impact most people, right? And the outcomes were, maybe counterintuitive for a layperson, but very intuitive for a statistician, in which that they obtained results that were very much aligned with the fact that the most people reporting these potholes and the most kind of alerts and whatever flags came from the kind of higher income neighborhoods. And it's because it's self-selection. I mean, this is not like especially for this audience, this is not an innovative concept, right? But it's the kind of pitfall that maybe someone coming through the ML and AI field from a more computer science background or a slightly different background is just not at the forefront of their mindset. Like it's probably because people were self-reporting more in those neighborhoods. The data collection was flawed. That the result of that prediction was the way it was, not because it really showcased reality. So these are some. But I guess my point is there are kind of clear technical, shall we say, technical statistical ML related reasons why these outcomes happen. And given that, that's why we've kind of moving away from the problem that we've discussed more into the solution space. That's why wherever there's like kind of clear technical failures, those failures usually have a solution, right? So it's not like we for a long time, I feel like the field just kind of said, oh, bias is so complicated. There's nothing we can do about it. But, there are things you can, if you can pinpoint the bad real world outcome and you can tie it to some sort of technical reason, there's a lot of reasons. They're complicated to find. They're complicated to define, what is right, what is wrong. But at the same time, you have a route there to kind of start working on it and improving on it. So our approach is very much, and the thesis of ethic and our thesis is that it's very much about, especially, shall we say, at earlier maturity stages, but even at later ones as well, it's very much about testing the system, right? So we see this, there's clear links between the problem, the technical problem, the real life problem. So we think that if you can test for the technical problem in these various areas of potential ML AI issues, then you should be able to, at least in part, identify these issues before they become like really problematic and mitigate for them to the extent possible. But for some reason, the space doesn't work like that right now. Right. So moving forward, okay, let's so it's not just this testing, testing is needed for the specific problems, but it has to happen in a certain way, or we feel that it is our thesis and our kind of, shall we say, not mission, but like our point that it should happen in a certain way. A lot of times the system is tested at the start of a pipeline, let's say it's a pipeline that, I don't know, part of it is like a lot of data pre-processing, some sort of, I don't know, manipulation, some sort of model, and then that's all productionalized, right? And the pipeline itself has a lot of steps before an inference actually happens. But what people do, or like not what is done right now, a lot of the times is that the input is checked and the output is checked. And by all means, these are important things to check, but then it becomes very hard to understand where the problem is, first of all. So if you don't check throughout the pipeline, if the pipeline is if not every single step is tested, usually the poor data engineer or the data scientist kind of tasked with solving the problem will have, okay, the output is a problem, but then they'll have to manually go back through the pipeline and figure out where the problem actually is, right? So that's quite time consuming. That's why a lot of times it takes time to fix the problem. So we say you should, from the beginning, test as much as possible throughout the pipeline. And secondly, there are some kind of real-life outcomes of the model that are not clearly seen in testing just at the output. Because if those pipelines are very complex, and especially if they have several steps of that have some sort of uncertainty element to them, like a prediction, like a PCA before a prediction, like some embeddings, a lot of different elements, and it's gonna be very hard to just test the output to understand if there's a problem or not. So yeah, that's the main the solution we think would work much better, and there's some specific testing patterns as well that we've as we've been working on this for quite a while now, and just on this, right? So we've figured out there's some ways to make testing much easier for us. So there's some patterns we could use, and I'm not going to go into that. There's more than these, but I'm not going to go into much details. Like, I think the key one is this metrics pattern, but there's quite a few more that using these patterns and a lot of the especially the bias identification methodology out there, you can incorporate in your testing suite quite easily. So when it comes to these metrics, a key way, again, this is just to follow what we've been talking about, the problem. A key way to come up with the metric is like, okay, you have your area of issue. The failure is usually, it doesn't have to be quantitative, but it's a question of finding a metric for a certain type of failure. So for performance, it's relatively straightforward to try to see, okay, are some segments underperforming, right? That is not hard. It's quite a straightforward metric. Okay, some of them are much more complicated, but it's a good start. For bias, for instance, you can see, okay, these two people look very similar on paper. They all have the same credit score, the same income, all of that, but they got different outcomes, and they happen to be a man and a woman. Clearly there's something wrong there, right? So then again, there's a metric for that. For drift, it's actually quite it's not straightforward, but some types of drift are quite straightforward to at least pick up there's a problem. The distribution obviously changes. So there's the metric. I mean, these are all statistics-based metrics. So I think there's nothing super creative here, but I think it's more the application of these metrics in a standardized manner, in an automated manner, and then hopefully playing around with these metrics. This is one pattern right out of many, but playing around with this pattern so that it really, the system really starts being observed and its failure picked up, as soon as possible, sometimes even before they happen, or like when they happen to a very small extent. So yeah, this is just a quick, I'm not going to spend too much time on it. I think I'm not sure, but we might have 5 minutes left. But
you have 3 minutes left.
3 minutes left. Right? Yeah, that's what I thought as well. Okay, so this is like a potential testing path, right? So if you imagine all the different steps in a pipeline, you want at each stage, this is focused specifically on bias and explainability, but you want at each stage to put kind of the relevant tests in. So from the data stage, and this doesn't include data collection, which you probably should, but even as soon as let's say a data scientist or someone gets the data, and they can start checking for proxies, they can start checking for sampling issues. It should be instantaneous. Then they move through the building of it. There's maybe they get to the end, there's some explainability tests to do, and then once they actually deploy it live, that there are some measures they can keep doing. And not only that, if their pipeline is quite long, they should have tests at every single step as well. So these are just some examples, but I will skim through it. But I guess it's the same. It doesn't matter really what the model is, this approach is applicable, because most models and most of these systems are built on this kind of pipeline approach, and maybe sometimes the steps are not fully sequential, and that's fine, but there's still an element of, testing these steps at individual steps and then seeing how the results correlate with each other. And is there a way in which, okay, if step 5 is showing me a problem, I can link this to step 2, and then kind of get to the solution a little bit faster. Great. And I guess on the kind of more ending note, so this is, very much like it's still very much a developing area, which is why with large language models, it's an unsolved problem that finally kind of maybe becomes more a thing in people's consciousness, but it's been a kind of not unsolved, but it's been an ongoing problem for a long time, and there's a lot of research areas, active research areas that are dealing with specific areas, especially, bias has cooled down a bit now, but I think it's probably going to pick up given the LLMs very soon. And I guess the last bit I just wanted to point out is that this is very much like an ecosystem type problem, right? So you can't just have, and especially now that, you're going to have regulation coming in, probably from the EU AI Act, probably not too much from the UK. I guess no one quite knows what's happening there, but certainly in Europe, there will be some waves of regulation. And this is not a problem that, we feel the testing element is very much a technical element that can be solved, at least partially, through these applying these tests throughout the pipeline that's being built at the technical level. But the problem itself needs all different teams around the business to work around it, because there is a interpretation. There usually is an interpretation level that pure data science, data engineering team might lack. There's also data collection element that is often outside these technical teams' remit, and there's a big regulatory and kind of business performance component that all these teams really need to come together to make sure that the outcomes I mentioned at the beginning, those negative outcomes, are being avoided and mitigated to the extent possible. So yeah, thank you very much. Hopefully there's going to be some questions. But yeah.
Okay, thank you. Does anyone have any questions that they'd like to put in the chat, or I'm not sure if you can raise your hand. You might be able to if you have a question. I don't think there's a question there. What I wanted to ask was, how can you be sure, you've talked about testing things, but can you be sure you can test what you're expecting, the biases that you're expecting? How can you be sure that you're going to uncover things that you weren't expecting?
Yeah, sure. So there are, we ourselves came up with an approach to do that, and it's basically an automated way to go through a variety of possibilities. But you're absolutely right. It's not straight. It's kind of, there are a vast combination of things that could go wrong, and the idea is that you start by testing for as many of them as you can, and then as the model becomes better, as maybe it's productionalized and you see it work, and things are working as expected, that you can remove a few of the tests and kind of remove the universe you're testing for. But that's why we like this approach, where it's basically, these are the areas, these are the pitfalls. You should be testing at least for these. Okay, there's a lot more, but to be honest, let's start from somewhere. Like, a lot of these things are not tested at the moment, and a lot of them, if you test, you'll find an issue. The issue might be deeper somewhere else, but they'll give you an indication that you need to keep looking and where to look.
Right. Okay. Thank you. Right. Well, I think the time's just about up, actually. So unless there's any other comments, but we can have some more comments generally at the end of the session. But I'd like to thank Raluca very much for that, and thank you very much for a very nice talk. And please stay on, obviously, and then we'll pick up some of the issues at the end of after the next two speakers. Okay, thank you. Sure. So my next invited guest, I'm very pleased to welcome Stelios Kampakis, and he's should be able to get his slides on screen. Would you like to share your slides, Stelios?
So hi everyone, I'm very happy to be here, first of all. I'm going to be talking about QIS in AI. Artificial intelligence is really the topic of our days. Everyone's talking about it. And it's clear that it's an incredibly powerful tool with many ramifications for society. And no one really knows where it's going to go in the next few years. Okay, so my talk is split in two parts. On the first part, I'm going to provide a very brief overview of artificial intelligence, explain a few things about its history, which may not be known to most people. And then in the second part, I'll talk about some quality issues that artificial intelligence is currently facing. I might briefly touch upon some potential solutions. But I think some of those points raised are going to make for a very interesting Q&A session, both for this talk and then at the final Q&A at the end of this event. So let's start with what is artificial intelligence. So artificial intelligence in the last few years, it's been largely treated as a part of data science, okay? So actually the term data science has dominated the landscape of data for the last 10 to 15 years. And it's really, this is a very nice graph, which I always like to use on these types of presentations. It was created in 2012, and it shows how data science is connected to different fields created over the decades, over centuries, if we include statistics into the mix, really. And how it really encapsulates all these different fields under one umbrella, okay? So obviously statistics was the first discipline to deal with data analysis. AI was a particular, let's say, vision, which we'll explain more. I'll explain more about this in the next slide. And machine learning and instantiation of the AI vision. And all these different fields, they're related to each other, either, for example, as being subsets like machine learning to AI, or statistics being a part of now data science, but also tangents to AI and machine learning. Tangent in the sense that it tries to answer similar questions in certain ways, but takes a different approach. Okay, so AI was created in 1956, as I'll explain in the first slide, but for the most part of the last few years, until really a few months ago, it was just treated as a subset of data science and largely as a buzzword, okay? And it's very interesting because AI has a long history as a discipline. It was officially created in 1956 in the United States as a collaboration between Carnegie Mellon University, MIT, and IBM. And the vision was to create some sort of thinking machine. And again, we're talking about an era during which different fields like philosophy, psychology, linguistics, neuroscience, they were overlapping to a large extent. Again, we're talking about 56, right? So this was before the advent of personal computers. And back then, the main approach was primarily based around using logical rules in order to recreate human logical thinking, okay, and try to solve problems. So one reason there was lots of overlap was that because the community in artificial intelligence and computer science was trying to borrow ideas from how the mind worked and then try to implement them in a computer in order to create thinking machines. Right. So as you might have guessed, that approach, it didn't go too far. It gave some interesting results, but nothing close to thinking machine. And by the 70s and the 80s, it largely fell out of favor. If anything, it became a toxic word, simply because many of the promises that the AI community made never really materialized. If I remember correctly, I think Neil Simon mentioned that he believed that the problem of AI would have been solved within one generation. Okay, where it seems now we're close to cracking it, but obviously it took more than one generation from the 50s in order to achieve that goal. So in the 70s and the 80s, that approach, they had some wins. It didn't go too far. The main win, I guess, of that era was expert systems, which again they never really properly took off. And then machine learning started being the dominant term in that area. So you can see in this timeline how artificial intelligence was the most popular buzzword, let's say, in that area, and for about 3 to 4 decades. And then machine learning started taking over. And then in the last few years, we have a particular subset of machine learning called deep learning, which now it looks as if it's going to become synonymous with AI through the use of transformer technology and large language models. So machine learning, again, for those of you, I guess for some of you might already know this, but for the sake of completeness, it's good to discuss this as well. Machine learning is a subfield of AI in the sense that it still tries to achieve some form of, let's say, artificial intelligence. However, when it was created, the intention was to take the opposite approach compared to traditional AI. So whereas classic AI, the objective of classic AI was to create these types of rules and logical systems to generate intelligence, the objective of machine learning, on the other end, was to use data and simple learning rules in order to achieve the same result. Okay, so Arthur Samuel in 1959, well before deep learning was discovered and well before machine learning became popular, he gave us this definition that machine learning is about giving computers the ability to learn without being explicitly programmed. Okay, so apparently this approach ended up being a very winning approach, simply because it's more efficient in certain ways. So in the 50s, 60s, and the 70s, the idea of creating logical rules and combining them seemed to be a very obvious solution to certain problems. However, it was very laborious, required lots of human input, and it couldn't scale very well. So as soon as we started collecting more and more data, and as soon as compute became more abundant, then machine learning essentially took over the world, which leads us to deep learning. Okay, so deep learning is simply a particular brand of, say, neural networks. Neural networks, again, has been one of those theories that has been around since the 20s, I think, or the 30s, if I'm not mistaken. The first neural model was by McCulloch and Pitts. But it was during the, I think, 70s, 80s, and 90s that they were studied. But neural networks, for the most part, were considered simply one more machine learning algorithm. And there was lots of debate as to whether they're useful or not. The main drawback being that they're not very transparent, something which is still true to this day. It's one of the problems with assessing the quality of these types of systems. So Geoff Hinton, who has been one of the most prominent figures in this field, and he is actually the person who came up with this term. And he largely came up with the term deep learning because neural networks had become a toxic term in the academic community because of the failure to materialize many of their promises. And the difference between the old school neural networks and the new neural networks was essentially the addition of more layers, inspired to a large extent by the way the brain operates. And apparently all these additional layers has the depth. They increase the computational power of these networks drastically. Hinton, interestingly enough, I thought would be very relevant to add this note here. It's very relevant to this talk. He recently quit Google, recently as in, I think, like 2, 3, or 4 weeks ago, something like that, warning over the dangers of the AI that has been created and the dangers of misinformation. Again, I think it's a very interesting point concerning the quality of those systems and coming really from one of the fathers of this technology. Okay, so deep learning is becoming synonymous with AI to a large extent, and since when we had the first breakthroughs, I think it was around 2010 or 12, its popularity has only been increasing. And the reason is that it has been applied to many domains that have traditionally been very, very difficult to crack. But there is an abundance of data like speech recognition, image recognition. And now it looks like the next frontier is generative applications, whether we're talking about language or images or video. And this actually gives faith to the AI community that we probably have cracked the code for general AI, at least partially. So this combination of deep learning plus some additional tricks like the transformer layers, plus an abundance of data and computational power, seems to be generating this effect. So you can see the power of this technology when it was applied in 2010 in speech recognition. So suddenly the error rate went from 22%, that was state of the art. At that time, it went to about 15%. So now we have close to perfect performance. Anything relating to images is now related to deep learning. And obviously now the most popular models, the ones that are being discussed, are around generative applications. So I'm sure many of you here must have seen this fake image of the Pope wearing this jacket, which at the same time is fascinating and worrying. Okay, and raises many questions about where this technology is, what this technology is becoming. And obviously, the main breakthrough, I guess, in terms of this technology and breaking into the mainstream was ChatGPT, and now we have the GPT-4 version, and now Google has also released Bard, and there are also many other models out there, some of them open source. So if you go to Hugging Face, you can find many open source models, either open source models like T5, open sourced by Google, or models which communities like Elefthero AI are trying to, they're creating in an attempt to reverse engineer ChatGPT and GPT-4. And this is essentially the first example of us having something close to general AI. Okay, so I'm sure you must have seen many of those examples floating around the internet. For example, the AI being able to analyze an image and then generate a description of it. This is another example here of GPT demonstrating some kind of logical capabilities. But again, there are countless examples. And something that's very fascinating is that now there's a multitude of books and courses and videos talking about this technology. And it's clear that we have created something. I mean, we as a research community in that area, it's clear that no one really understands its potential or limitations yet. This is another slide that proves this, but also raises many questions in terms of the quality of the output and how and what impact this output can have in different applications. This is a table that shows the performance that each one of those algorithms achieved in all these different standardized exams, like the SAT, and I think, yes, the uniform bar exam for lawyers, and a few other different exams. So in any case, you can see that the performance of this algorithm is actually quite good. It passes, I think, all of these exams. In some cases, the performance is actually quite high in the top percentiles, which is quite fascinating. And large language models are constantly evolving. Now the focus of the AI community is in that area, and it has been a game changer. It has been a game changer not only in the applications, but also in terms of how the user can interact with this technology. Because something very interesting about this technology is prompting, is the fact that a user can interact with this technology using natural language, which means that this technology is very open to anyone and doesn't really require a data scientist or an AI expert to use, which again increases the importance, the significance of this technology, while also raising some questions about quality. And now we're going to talk about some quality issues and how we can, some of the discussions which are going on in this space. I believe these are the main issues, but I'm not sure if any of them have any conclusive solutions right now. And that's why they are very good candidates for a Q&A session. And I do believe that over the next few years, we're going to be hearing about each one of those points more and more often. The first point, which obviously is something that's true not only for artificial intelligence, but I think is true only for AI systems, and I don't think it's going to go away anytime soon, is the problem of bias. So it's a problem that answers, I mean, in the context of large language models, there's lots of conversation around whether large language models have certain filters in place, whether they're biased against certain minorities, but also there are many users who are actively trying to make those networks speak in a particular type of fashion, okay? And again, it's a bit of a complicated problem because, first of all, we don't really have access to the full data set that was used to train this type of large language model. So we don't know where bias would enter into this process because it always starts with the data. And then this attempt to try and stop bias by adding those filters is a bit problematic because maybe these biases, these filters, they're biased themselves. And in certain ways, they can be bypassed through this form of prompting jailbreaking, okay, where you're like, oh, for example, this is the example I'm trying to show here. This is a jailbreak in action. If you ask ChatGPT to pretend that it is someone or to write about a particular topic in a certain style, then you can bypass any filter you like. Okay, so I'm not sure why this happens, but it's very interesting. So that's like one general issue, and obviously this is going to relate to the issue of spreading misinformation, and also this leads us to the next point, which is transparency and explainability. This is a very common theme in machine learning. Not all algorithms can actually explain their workings. Not all algorithms are easy to understand. And in certain cases, this explainability can be very, very important. Okay, there have been many cases in the past where, for example, the lack of explainability actually ended up being causing very serious incidents. Like there's this very famous story, I think, with, what was it, Amazon, that they wanted to create a machine learning system to help with recruitment, and that system was biased against females because the dataset contained a very small number of female candidates, and then this carried over to the way the machine learning system was making predictions. And I guess this was a side effect of using algorithms without really trying to figure out how they're making decisions. So in transformers, which is the underlying technology of large language models, we do have the possibility to, for example, to create these kinds of graphs which show where an algorithm focuses on while they're parsing like an answer. So again, ChatGPT doesn't give us this ability, but we know that it is possible. Like, for example, you could play around with the model of your computer. You can create these types of graphs. Nevertheless, it's still not as straightforward. So I think this is like a very common concern, which, even though the explainable AI community is growing and it's growing in size, and there are new techniques coming out, I think now large language models and AI, they just create a whole new set of problems around that area. And then intellectual property is another concern. This goes back to the training set, but also privacy concerns. I'll explain why in a second. Both ChatGPT and Midjourney, for those of you who don't know, is this service where you can generate images by using a description. You say, hey, can you create an image of, I don't know, like a spaceship or something cool, and then it can generate any kind of image you want. And obviously, many of those these networks were trained on material, some of which was copyrighted. And a concern in certain cases is that they might actually spit out output, which is exactly the same as the training input. So maybe, for example, they generate an image, which is the image of a real person. This is something, so at the same time, we have an issue of intellectual property, but also potential privacy breach. So imagine, for example, if someone can jailbreak Midjourney, and then somehow by doing this, they can extract some of the raw data it was trained on. Okay, so this would be actually a data security, data privacy nightmare. Again, so we're not, again, it's like a serious concern, and we'll see how the space will evolve. Probably this will require some form of regulation. I'd say in the short run, being a bit more pragmatic, because this technology is now being actively used by users all over the world. I think some of the most common, I mean, I've not been through a list of the most common use cases, but I'd guess it has something to do like with creating, for example, emails and documents and things like that. One of the problems is that quite often this technology might give incorrect information. It works on an associative manner, which means that it identifies associations between concepts and words, but it doesn't necessarily have a database of facts saying, hey, this is what, this is true and this is false, and then I have to correct my answer and so on and so forth. Which this associative nature of those networks leads to a phenomenon called hallucination, which is simply AI jargon for imaginary responses. Like it provides some dates which are flat out wrong about certain historical events that maybe they never happened, or maybe it imagines products and websites and similar entities which do not exist. Okay. Which obviously is something really troublesome if this increases the spread of misinformation. And also there are some ethical considerations and regulatory compliance. If anything, I believe each one of the previous points raises some concerns which probably regulators might try to tackle sooner or later. And it's really a very long list of topics. So obviously, besides the quality of the answers, the spread of misinformation, bias, etc., there are some more urgent concerns. For example, what's going to happen in the professional landscape? Are jobs going to be replaced by others? And also, who should be the user, right? So, for example, we saw how unpredictable certain times the responses should be. So, what does a ChatGPT for schools looks like? Should it be accessible by everyone? And I think it's very early in this stage, and I wouldn't be surprised if in the next 5 to 10 years we see some form of, let's say, GDPR for AI systems. And here are some examples, some guesses as to what we might see in the future, and I will be more than happy to discuss your opinions during the Q&A session right after that slide. I do believe in the very near future there will be some legal requirement to be able to check aspects of the quality of an AI system, and we might see some kind of quality engineer, AI reliability engineer, or something of that sort. Okay, I think. Or maybe someone who is checking a fact or something like that. Then secondly, I think there's going to be probably some kind of framework similar to GDPR, but focused on AI systems. One can be used as training data. And then in terms of transparency and explainability, it's still a new space for this type of technology. It's something I've read a few things about, but I don't really have anything concrete to show you right now, but one of the coolest, ways I saw, one of the coolest solutions I saw in that space is asking the network to explain how it works. Okay, so which is really this image that you see on that slide. It's essentially shows this process. Right? So I just went to ChatGPT and I asked, hey, can you explain how you make decisions? Okay, so it gives a very high level answer. So I don't think this particular answer gives, it's correct in the way that it describes how it works on a high level without really using mathematics or anything too complex. But it would be more interesting to see whether eventually this technology will be able to say, hey, I gave you this answer for those reasons. These are the data points which are relevant to this answer. These are like my references, and so on and so forth. But in any case, the future is unpredictable and exciting. So that was it. And let's move on to the Q&A. Thank you.
Okay, thank you very much, Stelios. Perfect timing there. So let me have a look in the chat if anyone has any questions that they've put in the chat. Or you might like to raise a hand. Otherwise, can I just ask a quick one while anyone else is thinking? You mentioned 1 trillion parameters in the ChatGPT. That's extraordinary. Are there issues? Well, there's over-parameterization, but I suppose there's even more data than that. And what about the interrelations between all the parameters, or is that not quite the way to look at it?
Oh, so with these models, there was actually a piece of research. Sorry, I have to find it. I can send it to you if you want. I think it was Google, where they tried to figure out what's the optimal size of the data for the number of parameters. These models have a ridiculous number of parameters because they process language across many different domains, right? So it's a lot like trying to replicate the human brain to some extent. So I wouldn't say they're over-parameterized in that sense. Based on the results we have, I'd say they're actually parameterized at pretty the right level. Probably the community figured this out through trial and error over all those years by increasing the data sets, playing around with different, different data sets of different sizes and different numbers of parameters. I think that the CEO of OpenAI, however, recently said that probably future research shouldn't just focus on increasing the model size, because it looks like we're reaching the limit. We're reaching some diminishing returns, and maybe they should focus more on actually making these networks more efficient. Okay, so but it looks like for a long time it has mostly been the case that more is better, both in terms of parameters and data. But I guess, yeah, probably in the next few years, we might observe the opposite trend, that trying to make these networks more efficient, easier to use in commercial applications, like to use, for example, on a mobile phone, and things like that. But again, like the problem with this, say with these models in terms of the number of parameters, is that if you come from a statistical background, then a parameter has a very concrete meaning. Okay, whereas in neural networks, you have these abstract units where they have a representation with many things going on in there, like regularization and bias and blah, blah, blah. And then you just have all these interconnected layers. And even for a small network, you could easily have 1,000 parameters, you know. So 1 trillion in this type of community is not like a huge jump.
Thank you. Could I just ask another question? Could you go back to the slide transparency and explainability? I think that's number 17, is it? That one, yeah. Could you just say what's going on in the bottom right-hand side, the quick brown fox bit? What's actually happening there?
Oh, so that's a visualization of the transformer architecture. So the transformer is this technology created by Google AI Labs, I think like 4 or 5 years ago. Can't remember the exact date. There was this seminal paper called "Attention is All You Need," where essentially what the researchers proposed was a type of neural network layer that could replicate human attention within a deep neural network. Okay.
Frozen.
Certain parts of the input when it's giving a particular answer. So this is quite revolutionary, because while you're translating a sentence, let's say from French to English, then if you want to translate, I don't know, the word fox to French, then you want most of the neurons to actually be focused on that particular word. And there were these visualizations showing how it all works. Probably it's difficult to understand unless you have the full context of the algorithm, because you see here it says query and key, and the q times k, and then q dot product k, and then a softmax. So what it's really, all this thing, it really leads to a number between 0 and 1 for each one of those words in a sentence. So then while it's generating the next word in a sequence, while it's translating, you can see for each one of the translated words, which words it was most focused on. Okay, and then you could clearly see, and back then it was a really cool technique, because you could see how, for example, the network had started to understand how the words match, the syntax, like what's the subject, the verb, this kind of thing. But again, it's not necessarily super transparent for someone who's not into coding these things. So I'm not sure if, for example, in a court of law, whether this would make any sense in that regard, if it ever came down to that.
Okay, thank you. There's a question in the chat. Just in a nutshell, how does artificial intelligence know the cause and effect is real?
I don't think it does. That's my answer. I don't think it does. Sorry, we're not there yet. Very, very smart question, and it's actually an issue raised by some people in this community, like Judy Appel, who has spent the last 10, 20 years of his career studying causality. I don't think it has this kind of understanding. I just think it's an associative technique on steroids taken to the extreme, which it's surprising how well it works. I think many people didn't expect it to work that well, to the extent that it looks like it's intelligent. There are certain ways to try and impose some form of causality by having like these connections which are like a directed acyclic graph, saying, you know, there's a concept connected to some other concept, but I don't think any of them are used in ChatGPT. I wouldn't be surprised, however, if, you know, they're running experiments to try and make the network understand these things, because I know that some of the ideas in this community, they're around, you know, mathematical, you know, proofs, proving theorems, and running experiments and this type of thing. So some understanding of causal reasoning would be quite important in that regard.
Thank you. Okay, that's our half hour up. Thank you very much. That's a really interesting talk. So thanks, Stelios. Brilliant. Thank you.